Chapter 5 Pattern Mergers Ahead. By this point, you already know everything you need for creating and reading a hex filtration chart of your own, even the strange, somewhat advanced stuff. So I guess there's nothing more that I need to teach you about this topic. However, there's still plenty I want to share. This chapter is only for the adventurous folk who want to know more than they need, which, in my opinion, basically means anyone reading this book. After all, who else would be reading it in the first place? If you remember in Chapter 1, I made quick mention that there are two methods available regarding the hex filtration concept. The fleshed out hexadecimal chart, which is easier for human use, and the single string of hex digits, which works best for computers. Now's the time to discuss the single hex string method. With this method, the hex pattern for every single row is built and placed exactly the same way as previously taught. The difference is with how they all get grouped into a single line versus having an infinite list of rows, each with an endlessly repeating pattern. Something interesting about this method is when each line is merged into the singular row, let's call it the master row, then each of the regular rows only need to be calculated to a limited preset number of digits. After that point, none of the digits in a row ever need to be calculated again. Okay, I expect this sounds a bit confusing. I've got no doubt that you're probably wondering, but how can the pattern stay accurate if you stop calculating rows? This is a legitimate conclusion, but no worries, it will work. The key to it all lies in the fact that instead of having each of the regular rows extend on into infinity, the master row is the only one with no logical endpoint. However, the master row is considered to have an accurate measurement of its prime numbers up to a limited number of digits based upon how many of the regular rows have been merged into it. Okay, now that you have the general breakdown, I want to offer a bit of caution. This method is intended for computers for a very good reason. There is much to consider when merging these rows together, as you'll see, I believe. I'll start with what might be considered the simplest aspect of this method, calculating the length required for each of the regular rows. This should be easy because all of the numbers are fixed based upon the number of your row times 2, then plus 1, and finally multiply the whole thing by the length of the previous row. For example, row 1 times 2 plus 1 equals 3, which in this case is the length necessary for our row because row 0 basically has a length of 1, which doesn't affect our row length. Next, row number 2 times 2 plus 1 equals 5. Multiply that length of row 1 and you get 15, which is the exact length necessary for row 2. I believe that this should be clear enough now, I hope. Just continue this trend for all the following rows when you get to them, and you'll be doing just fine. Now that you can calculate row length, it's time to figure out how to determine each row's starting column and final column it will expand out to. Maybe you think, this is pointless. I don't need to calculate each row's last column number. Well, in this you may be right. It is simple and maybe a bit pointless, but let it be chalked up as my attempt at being thorough. It actually takes virtually no effort, so don't expect any examples. Here you go. Find the row's starting column number, i.e., row number times 2 plus 1, then square it all. Finally, subtract 1, then divide by 8 and drop any decimals. When you have the starting number, simply add it to the row's length minus 1. Simple. Next, the slightly more tricky stuff, the actual merging of each of the rows one at a time into the master row. In order for me to clearly explain this part, I need to be sure you understand a little something about binary mathematics. The concept is simple enough. How can binary ones and zeros be merged in such a way that they will return a rational mathematical result? Well, as it so happens, this concept has a logic well that runs so deep, you could probably drown in it. The binary concept that I am borrowing from is a bit of computer logic called a Boolean AND function. Let me scroll this up here real quick. It is the same stuff that physically makes microcircuits work. Anyway, This isn't a microcircuit tutorial, so I'll move on. I use the hex/binary association to Boolean and merge each of the hex digits into the master row. Please check out example table number 2 for now. Table 2 is a complete presentation of how every hex digit merges based together upon their associated binary digits using the Boolean and logic method. It's really beyond the intended scope of this book to try and go into any depth as to why this particular Boolean method works, but take it from me, it's an established and well-used concept. It works. I'll leave it up to the more determined folk to explore the reasoning behind why it works in some other specialized computer book. At this point, I figure it's absurd to assume that none of you inherently know how to use the table I've provided. I can't believe anyone who doesn't get it would ever be able to make it this far in a book such as this one. And the place where any given digit column and row cross has the resulting hex digit value of the Boolean and calculation for those two hex digits. Okay, so assuming you have no problems with it, it's time to merge the regular rows into the master row. Finally, and I suppose maybe a bit obviously, merging the digits is stupid simple. Just start at the beginning digit of a row and merge it into the master row of the same column using table 2 as reference. The only cinch is to always remember that when you have finished merging a row's pattern length into the master row, the new pattern is basically assumed to continue on forever, into infinity until the next row is merged into it, creating a new pattern. As an example, we have already established that the length of row 1 is intended to be simply 3 digits long. However, logically speaking, until row 2 is merged into the master row, the pattern created by row 1 just endlessly repeats itself. In fact, at this point, if you never bothered to merge any new rows into the master row, you could still read the master row digits and pick out which of the correlating base 10 digits are not prime, as well as which ones could still be prime down the line. In fact, even at this limited number set, the master row is actually accurate enough to reflect a certain number of base 10 digit prime values. Well, only for 3 of the hex digits for row 1, but they are accurate nonetheless. Each time you merge a row into the master row, the accuracy increases within the master row. So how do you determine the number of digits in which the master row is completely accurate? Well, that's simple. Just use the starting column number of the row following the one you just merged minus 1. So, for example, once you have merged the first 15 rows, then the first 135 digits of the master row will completely reflect the prime value for all the base 10 digits they correspond with. Neat, right? I figure you might notice that this requires a hell of a lot of work just to get a few accurate hex digits, and you're correct, if that's how you want to view it. However, please consider the fact that each newly created row merger pattern, though hardly complete, is still providing a significant amount of information that helps tremendously when calculating, let's say, that huge base 10 digit down the road. Basically, it reduces the amount of work necessary to determine if an unknown number is prime. This is where cool concepts like the fraction mass come into play, and being the deviant little entertainer that I am, I'm going to let you figure that a little tidbit out for yourself, as you should be able to do so by now anyway. One last thing. The master row pattern is basically intended to be used as a kind of database reference set. It is impractical to assume that this would be used exclusively as any kind of valid human-level calculation method for prime numbers. This technique, however, allows for a kind of shortcut to reduce the workload with massive number searches. For example, an internet domain program for prime number searches could possibly benefit greatly from this because the master row pattern can be easily looked up without much effort. It obviously would need to be pre-calculated, but since it reflects a basic pattern, every number will follow it. It is perfect for very large number searches. That said, I have to tell you how the master row pattern lookup works. Let's try to determine if the base 10 number 1767 is prime. Well, that's a bit more difficult with the lessons I've taught you so far because it's outside the example hex chart I provided. But using the master row pattern, it becomes somewhat easy. First, you need to determine which column the chosen number is found in, i.e. 1767 minus 1 divided by 8 equals 220. Then you need to subtract the starting column from the most recent row you have merged into the master row. Well, because I'm a bit lazy and this is only an example, I'm going to calculate with up to row 3 merged into the master row. So, since row 3 starts at column 6, you get 220 minus 6 equals 214. Next, like in chapter 4, if you remember, we need to mod our number by the length of our established master row pattern, which if you were following closely in the previous section is 105 for row 3. Thus, 220 minus 6 mod 105 equals 4, and the fourth digit of the master row pattern is 6. For anyone willing to work this all out, it proves that the number 1767 is not prime. If for some reason, however, the number you are looking up ends up having a hex digit of, let's say, F from the master row, then we would have had to calculate out each of the following rows, at least as far as the fraction match for that column requires, until the number was determined to be prime or not prime. Okay, master row pattern merging flowchart. Without any rows merged into the master row, it is assumed to contain an infinite pattern of repeated hex F digits. Row 1 starts at column 1 and contains the pattern 6dB. When merged into the master row, the 6dB pattern repeats itself forever and leaves column 0, 1, and 2 in perfect accuracy, i.e., none of the primes found in these three columns are considered potential, whereas the remaining infinite columns in the pattern simply reflect the placement of potential prime number positions. The infinite columns pattern, however, does inherently reveal many unchanging non-prime number positions as well. Row 2 starts at column 3 and contains the pattern 7, B, D, E, and F. But because of required convention, we must repeat this pattern until it has 15 digits in it. Thus, row number 2 must be merged as 7B, D, E, F, 7B, D, E, F, 7B, D, E, F, plus the pattern from the master row of B6D, 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 B6D. Merged together, the pattern is 32D, A65, B4C, B69, 96D. When row 2 is merged, the master row pattern is changed from column 3 onward with columns 0, 1, 2, 3, 4, and 5 in perfect accuracy. This leaves the remaining infinite column numbers with a new pattern of now 15 digits, i.e. A65, B4C, B69, 96D, 32D. Every single row has a pattern that can be merged into the master row with this method. Why don't you give it a try? Hint: remember to multiply the established pattern length with the next row's pattern length. So for row 3, whose length is 7, i.e. row number times 2 plus 1, you must multiply it by the 15 from the master row's pattern length and get 105. Then multiply row 4's length by 105, etc. forever. Just in case you missed it, the master row is always accurate up to the starting place of the starting column of the row following the most recently merged row.